Hello, welcome to Technoveda Solutions.
In this video, we will discuss about the PWM operations using a STM32 microcontroller. So for the PWM operations, we'll be using timers. So let's see how do we configure the timer to work with the PWM mode, and what are the other configurations to be done with the GPIOs, and how do we implement the PWM. Now, first we have to include header files. That is, one is standard integer and another is STM32F4XX. As we are using a CMSIS method of coding, we need to include this header file. Then here we can see prototyping of the functions. Then in the main function, we just call the PWM configuration function, and then we call the function where we will be passing a certain parameters. So this function we'll see how it works a little bit later. Right now, first we'll understand how the PWM configuration is done. So let's go to that function. So this is a PWM configuration function. Now we want to use timer 3 in a PWM mode. Now, on what basis did we choose that we want to use a timer 3? So now it depends on what GPIO we want to use and how that GPIO is mapped to a particular timer. To understand the mapping of that, we will go to data sheet and understand the mapping of alternate functions to the GPIOs. So in the data sheet under pinouts and pin description, there is alternate function mapping table. In this table, we can see how the pins are mapped to different alternate functions. Now here we want to have a timer. So let's take PC6 as an example for our operation. So suppose if I choose PC6, if I just zoom it, you can see here the PC6 is mapped with the timer 3 channel 1. So this is mapped to alternate function 2. So now I have to configure PC6 in alternate function 2 to operate it under the timer 3 channel 1. So now once we see the mapping table, how the mapping is done between the PC6 and the timer under which alternate function, then we can just go to a data sheet and go to a GPIO registers. In GPIO registers, first we enable the port C. So this is enabling the port C by shifting 2 times in the AHB1 ENR. So if you are not familiar with how the modder or the AHB1 ENR or any GPIO configuration, you can just watch previous videos. You will have a clear picture on that. Now here we are enabling the port C, and then we want to configure GPIO-C pin number 6 in the alternate function mode. Now this is a pin number 6 which we are configuring in the alternate function mode. So this is not output mode, this is alternate function mode. So for that, 10 is configured to pin number 13 and 12, that is sixth pin of GPIO-C. Once we configure the PC6 in alternate function mode, then we have to configure in which alternate function it is going to work, because we saw in the data sheet that there are so many different alternate functions. Basically, there are 16 alternate function AF0 to AF15. Now we have to tell which alternate function we want to use. Here we want to use alternate function 2. So to configure that, we have to go to a AFR register. Now we know that in the AFR register there are two different registers, AFRL and AFRH. AFRL for the lower byte of the pins and AFRH for the higher byte of the pins. That means the pin number 0 to 7 are mapped in the AFR0 or AFRL, and 8 to 15 are mapped in the AFRH or AFR1. So now here we are using AFR0 because the pin what we are using is PC6, which comes under lower byte. So in that, if you see a data sheet, this reference manual, and if we go to a GPIO registers, and if we go to AF0, AFRL, which is AF0, Here we can see that the pin number 6 is from 24 to 27 bits. 4 bits are there. For each pin, there are 4 bits mapped. Now we want to configure in AF2, that is alternate function 2. So I have to configure 0010 in pin number 24 to 27. Why AF2? Because in the mapping table, we have seen that it is the alternate function 2 in which we want to operate for the PC6. So pin number 6 we will be configuring 0010. For that we are shifting value 2, that is 0010, to the bit number 24. So now in the bit number 24 to 27 will be set 0010. That means we have configured GPIO PC6 in alternate function mode, that is AF2. First we have selected the mode of operation and then we configure the alternate function. Then we have to check where the timer is connected. Now our timer is connected to APB1. So we go to enable registers of APB1 and we enable the timer. We can see in the APB register, if we go to RCC register, in that if we go to APB1 ENR, so this is the APB1 ENR. If you want to have a timer 3, then this bit has to be enabled, that is bit number 1. So in the code will be 1 shifted 1 times, that will be bit number 1, which is enabled though. That means the timer 3 is enabled. Here we are prescale and count we are keeping it 0. So the description of PC and CNT you can find in the timer operations of other LED blink or counter operation. You can go through that. There I have explained completely about prescaler register, what exactly PSC is. Now as we want to work a timer in the capture and compare mode register, so this is basically a compare output compare register mode what we want to work. So we'll be using CCMR register here. Now let's go to CCMR registers in the reference manual. So if we go to timer 2 to timer 5 registers, in that if we go to CCMR, so this is CCMR1 register. In that the bit number 3 is used to enable the preload enable. We can see bit number 3. Now we can observe here from here to here, that is bit number 0 to bit number 7, it is for channel 1. So we are using the channel 1 itself. So because we have observed in the data sheet that our timer 3 we are working in the channel 1. So in the reference manual we have to go through these CCMR register. So we are going to work with the channel 1. So these bits we have to configure. These higher byte bits are related to channel 2. So we can see here it is 2 is mentioned, here it is 1. So this is channel 1. So in that I want to enable the output compare. So this bit will enable output compare with preload. Output compare channel 1 preload enabled. So we are going to enable the preload. Once we do that, then we have to set the CCMR in the PWM mode because we want to work timer under PWM mode. So for that we have to set the configuration in the output compare mode. Now if we scroll down, that is bit number 4 to 7, if we see 4 to 6. So here we can see the PWM mode is 110, that is in the mode 1, that is in the PWM mode. So for that we will be configuring these bits as 110. That is 6 is shifted 4 times. So 110 is configured for the PWM operation. Then we enable the register CCER, that is capture and compare mode enable register. So in that if we see CCER capture and compare enable register, in that we want to enable the bit, that is we are shifting 3 to bit number 0. So that means we are setting CC1P and CC1E. So we are enabling and we are setting the polarity normal. So here you can see the bit descriptions. So bit number 1 is output polarity. We are setting it active low, and here we are enabling the compare mode because we are using it in the compare mode. So we are enabling the compare mode. So these two bits will be set to 1 1. Now once we do all these configuration, then we will start the timer using CR1. We know that CR1 bit number 0 is for to start the timer. Just let's verify that. So here we have enable bit. So this bit will be set to enable the timer. So these configuration we have to do with the timer 3. Once we are done with the configuration, once this function is successfully done, then inside the while loop, we are going to generate the duty cycles using a PWM method. To generate a duty cycles, we have to send certain parameters. That is, three parameters will be sending: frequency, duty cycle, and channel. However, don't confuse this with directly a frequency. This will be a value sent, and based on this value, the value of the ARR will be calculated. So we'll go to that function. So now if you come to this function, here you can see the frequency variable will carry the value what we have sent from the function. Now based on that, the ARR value will be decided. So once we decide the ARR value, as we want to have a PWM, let's keep the ARR value common for all the three things. Now only we are going to change capture and compare register. CCR1 we are going to configure, or we are going to change the value in CCR1. How do we change that? That will change based on the duty cycle what we sent, because we are keeping ARR same for all the three calls. You can see we are calling this function 3 times, and we are keeping the value of frequency variable or FREQ variable constant. That is same value we are sending here. So ARR will be same for all the three calls, but the duty cycle what we are sending is different. You can see once we are setting 90%, then 40%, then 10%. So we can send any value between 0 to 100 in the second parameter. Channel, this is just a generalized function. So anyway, we are using channel 1. So if we are using a different channels, then this makes sense. Otherwise, we can just ignore it for a while. So here, based on the ARR, the CCR1 value will be calculated. Now, whenever the capture and compare register becomes equal to the CNT register, that is when the timer is triggered or overflows. Timer overflows at that instant. So based on that, the width of the waveform is going to change. Now let's compile the code. Okay, now once we get the hex file, let's go to simulation using Proteus. So here we have configured the Proteus. Here I have configured the Proteus with STM32F401. So you can observe that the same microcontroller should be selected in the STM also, 401RD6. So the microcontroller should match, otherwise the simulation may not work. So now to observe the actual changes in the width of the waveform, I have connected the oscilloscope here. So oscilloscope is connected to pin number 6, that is PC6. This is where we are generating a PWM waveform. So let's run and observe the oscilloscope. Let's run the code. So now if I run the code, oscilloscope is automatically open. Now you can see it is off for the 90% and on for the 10%. So duty cycle, the period what you have sent, that is off period. So it is off for 90% and it is only on for 10%. Then after some time, you can see the pulse width will automatically change. See, now it is on for 60% and off for 40%. So that is the next waveform. So you can observe here, first I have sent 90, then 40. Again, after some time, it has to come to 10. Now the next step should be 10%. Now you can see it is 10% off and 90% it is on. So similarly, let's just stop this and let's change the duty cycle and observe, or we'll just add one more duty cycle. Say for example, I will add a couple of lines here and I will say 20%. And then let me compile the code. So hex file. So now I will reload the hex file because I have compiled it again. So now I have reloaded the hex file. Let me run the code. So now I am expecting 20% also. So right now it is coming 90% off and 10% on. Then the next we are expecting 60% on and 40% off. So now it is 60% on and 40% off. That's a second function call. In the third function call, we are expecting 20% off and 80% on. So now it has to again change to that 20%. So after a particular delay, it will change. So we are waiting. Now you can see it is 20% off and 80% it is on. Now it is then the another function is 10%. Last one is 10%. So that is 10% off and 90% it is on. So we have called it 4 times. So this is the off period what we are sending here. So remaining period it will be in the on state. Only for this period it will be in the off state. That is the PWM will be in the logic low and remaining it will be in the logic high. Depending on the requirement, we have to send the off periods here. So we can observe the continuous changes here. So I hope you've understood how the PWM work. Thank you for watching the video. If you've liked the video, please click on like button, subscribe to the channel, and